What's up, guys? My name is Michael and welcome to my YouTube channel. And today, congratulations, guys. We have done this full 3-week intensive introduction to C++, and now we have a solid understanding of C++. But in modern programming, there's always more to learn. So this final lesson, we're going to do some missing details that we never talked about, that we just briefly skipped over. And today we're going to learn what conditional compilation is, how to manage it, how to write macros using the preprocessor, how to use the preprocessor to find bugs, and how to manipulate individual bits and use them as flags, and what the next step to learn C++ effectively. So, what is a preprocessor? The preprocessor, every time you run your compiler, your preprocessor runs first. The preprocessor looks for the preprocessor instructions, each of which begins with the pound symbol, hashtag, right? The effect of these instructions is to change the text of the source code. The result is a new source file, a temporary file that you don't normally see, but you instruct the compiler to save so you can examine it if you want to. Compiler does not read your original source code file. It reads the output of the preprocessor and compiles that file. You've seen this effect already with the include hashtag include directive, and this instructs the preprocessor to find the file whose name follows the hashtag include directive and to write it into the intermediate file with that location. It is as if you had typed that entire file into your source code, and by the time the compiler sees the source code, the file is included there. So you could use a preprocessor like this, hashtag define. You can create string substitutions with the hashtag define command. You write hashtag define big 512. This basically substitutes every time you see big, it replaces it with the 512. You have instructed a preprocessor to come the string 512 whenever it sees the string big. So every time it sees big, it substitutes 512 in it. This is not a string in the C++ sense. The characters 512 are substituted in your source code wherever the word big is seen. Thus, if you write int my array big, the immediate preprocessor file would look like this. Note that the hashtag define statement is gone. The preprocessor, the pre-compiler statements are all removed from the immediate file. They do not appear in the source code at all. So you could use hashtag define for constants. It's a good substitute for constants. This is almost never a good idea though, because hashtag define merely makes a string substitution. It does no type checking. So a better advantage to use this is use the const instead of hashtag define. Okay, so you can use hashtag define for tests. A second way to use it is use for tests. You could declare a particular string is defined, therefore you could write hashtag debug, define debug, and then later in your listing you can test whether a big has been defined and take action accordingly. To check if it is defined, you can use hashtag if command followed by define command. So you could say hashtag if define debug, then print debug define, and then hashtag endf. The define expression here evaluates the true if the name it tests debug in this case has been defined already. Keep in mind that this happens in the preprocessor, not in the compiler or in the execution program. When the preprocessor reads the if define, it checks the table it has built to see whether you've defined the value that follows. If you have, the define evaluates the true, and everything between the hashtag if define, debug, and the hashtag endif is written into the intermediate file for compiling. If it evaluates the false, nothing between hashtag if, define, debug, and hashtag endif is written to the intermediate file. It is as if it were never in the source code in the first place. So a shortcut directive also exists for checking define values. This is the hashtag if define directive, which does the same thing. And you could also see if it's not defined, just do hashtag if, exclamation part, define is not defined. Okay. And you could do another shortcut, which is hashtag if n define debug, which checks if it's not defined. Oh, you also could use the else. Else can be inserted between if defined or if not defined and the enclosing end if. These could be used like this. So you have hashtag if defined demo version. If demo version was defined, it would print out this. Otherwise, print out hashtag demo version is not defined, and hashtag endif. It's the same thing. These are good for like debugging purposes. So demo version here, demo version is defined, the test is true, and the string is put. Okay. So yeah, the windows you did not define Windows version show a failed to print. Okay, so There's also inclusion and inclusion guards. You will create projects with many different files. You will probably organize your directories so that each class has its own header file. For example, .hpp with the class declaration and its own implementation file. For example, .cpp with the source code for the class methods. Your main function will be in its own .cpp file, and all the .cpp files will be compiled into an obj file, which will then be linked into a single program by linker. So because your programs will use methods from many classes, many header files would be included in each file. Also, header files often need to include one another. For example, the header file for a derived class's declaration must include the header file for its base class. So imagine that animal class is declared in the file animal.hpp. The dog class, which derives from the animal, must include the file animal.hpp in dog.hpp, or dog will not be able to derive from animal. So the cat header also includes animal.hpp for the same reason. So when you create a program that uses both cat and dog, you will be in danger including the animal twice. This generates a compile error because it's not legal to declare a class twice, the animal class twice. So to solve this problem, just do this. At the top of your animal file, just write if it's #if not define animal underscore hpp, then define animal underscore hpp. Then the whole file goes here. Then do #end if. This says if you haven't defined the animal.hpp header file, go ahead and define it now. Between the #define statement and the enclosing end if are the entire contents of the file. The first time your program includes this file, it reads the first time and the test evaluates the true. That is, you have not yet defined animal underscore hpp. It defines it then and then includes the entire file. The second time your program includes the animal.hpp file, it reads the first line and the test evaluates the false because you already included the HTTP file. And the preprocessor doesn't include any lines that reach to else. It skips the entire concept file and the class is not declared twice. This is actually very important because of the actual name of the defined symbol animal underscore hpp is not important, although it is customary to use the file name in all uppercase letters with the dot changed to an underscore. This is purely convention. However, you won't be able to give two files the same name, and this convention works. You can also use macro functions. #define directive can also be used to create macro functions. A macro function is a symbol created using #define. It takes an argument much like a function does. The preprocessor substitutes the substitution string for whatever argument it is given. For example, you can define the macro twice as #define twice x times 2, and then in your code you write twice 4. The entire string twice 4 is removed and the value 4 times 2 is substituted. When the precompiler sees 4, it substitutes 4 times 2 and then evaluates the 4 times 2 or 8. A macro can have more than one parameter, and each parameter can be used repeatedly. In the replacement text, two common macros are max and min. So you could create a macro like this and then use this. It's like a function, and you can now use the macro max min max xy. Note that macro functions definitions open parentheses is for the parameter list. Must immediately follow the macro name with no spaces. Preprocessor is not for forgiving of white space as its compiler. If there is a space, a standard substitution used, as you will see later in today's lesson. So now, because you define the max function like this, if x is greater than y, then the maximum value is x, otherwise it's y, from this ternary operator. Because we define this, you can now use the max function like that. You could do pass in x and y, and then z would be that. And that's what it does. It replaces the code right in here. So after the substitution, rather than invoking the macro function, the max has been substituted, and that is followed by this, followed by max. By removing the space between the max xy, however, the intermediate code becomes this, and this evaluates as 7. So yeah, that's spacing matters. Just make sure you do it right for your spacing. Why all the parentheses? You might be wondering why there's so many parentheses in macros. The preprocessor does not demand that the parentheses be placed around the arguments in the substitution string, but the parentheses help you avoid unwanted side effects when you pass complicated values to a macro. For example, if you define max as this and pass in 5 and 7, the macro works as intended. But if you pass in more than complicated expression, you receive unintended results. So here they have a macro cube. and they just multiply a 3 times, and then they have the hashtag the macro 3, a macro function of 3, and they don't put parentheses here. So then now they call cube, and then now they call 3. So this y should be 5 times 5 times 5, which is 125. 3, it should also be 125 because they multiply 1 3. But the problem is here, yeah, it is 125. Yeah. But they make it complicated by adding 5 plus 7, right? So this should be 12 times 12 times 12, and these both should be 12 times 12 times 12. However, the second one is not. Let me just see what 12 times 12 times 12 is. 12 to the cube. It's supposed to be 1728, right? So for y, it's correct, but for z, it gets strange. It prints out 82, and there's a reason why it does that. So first line evaluates it as a parameter. So the cube expands it like that, which evaluates to 125, and which also evaluates to 125. However, the second line, in the case of the cube 5 plus 7, evaluates to 5 plus 7 times 5 plus 7 times 5 plus 7, right? And this evaluates to 12 times 12 times 12. But 3 evaluates this, and because multiplication has higher precedence than addition, it becomes that, which becomes 82. So if you don't put parentheses, you could actually screw a lot of things up, because they do multiplication first, and that's why 3 prints out a different value for 3 for here z. It's not 1728. These values should be the same thing, but it's not. And the reason it isn't because they didn't put parentheses, and it caused the multiplication to be done first instead of the addition, which caused this problem. This problem evaluated to 82. So yeah. You also could do string manipulation. They provide 2 special operators for manipulating strings and macros. The stringanizing operator substitutes a quoted string for whatever follows a stringanizing operator, and the concatenation operator bonds 2 strings into one. So you could do this. Stringanized operator puts them up to the white space. So you could write hashtag define white string x, and then cout hashtag x, and then when you call write string, this is a string, it actually puts them all into a string. So you could define your compilation like that. The concatenation operator allows you to bond more than one term into a new word. The new word is actually a token that can be used as a class name, a variable name, and offset into an array, or whatever else a series of letters might appear. So assume for a moment that you have 3 functions aimed: f1 print, f2 print, f3 print, f4 print, f5 print. You can then declare hashtag define fprint x as this, and then you could use fprint to generate fprint3 and fprint4. So then during remember the parts list, this list can only happen objects of types list. Well, you might want to make a list of animals and cards. So for one approach is to create an animal list, card list, and so on, cutting and paste the code over and over again. This quickly becomes a nightmare, but an alternative is to use macros and concatenation operator. For example, you could define hashtag list of type class, and then type hashtag list, and then do all this. And then this example is overly sparse, but the idea is that you put all the necessary methods and data, and then when you're ready to create an animal list object, you write list of animal, and then it basically just creates your animal object. But just don't do this. Some problems can occur because of this. You could also have predefined macros, which are just like, these are macros that the compiler already knows what happens in the code. So like the preprocessing macro makes this necessary substitutions for like underscore date, underscore for the time, underscore time, underscore line, underscore file, and they all tell you what if you put this, it substitutes the right thing for it. Okay, you also have the assert macro. This returns true if the parameter evaluates to true and some kind of action. If it evaluates to false, many compilers abort the program on assert that fails, and others throw an exception. So the assert macro is used for debugging before you release it. So in fact, if debug is not defined, the preprocessor collapses the assert so that no code from it is included in the general source for the compiler. This is a great help during development and when the final product ships, there is no performance penalty or increase in the size of the executable version of the program. So rather than depending on the compiler provided assert, you are free to write your own assert macro. And here they list shows how you could write your own assert macro like that. Hash not defined. But basically, assert is like it does the condition if the thing is true. Like sometimes if it's false, it might throw an exception and stuff like that. So when you write a program, you will often need to know what something is true. A function has a certain value, a pointer. So nature of the bugs that you know might not go under some conditions. For example, you might know that a pointer is valid, yet the program crashes. Assert can help you find the type of bug, but not only if you make it a regular pass, you use assert in your code. Every time you assign or pass a pointer as a parameter, be sure to assert that the pointer is valid. So every time your code depends on a particular value being a variable, always use assert that is true. Because then, yeah, there's no penalty for using assert many times. It is removed from the code when you define debugging. It also provides good internal documentation of telling what happens. So we talked about exceptions, right? So assert is created to catch programming errors only. If an assert fires, you know you have a big bug in your code. This is critical because when you ship your code to your customers, instances of assert are removed. You can't depend on assert to handle a runtime problem because assert won't be there. So a common mistake that people use is assert to test a return memory from a function. This is an error, okay? Because every time the programmer runs the program, the memory is available, and assert never fires, okay? And after all, programming is running with a lot of extra RAM to speed up the stuff. So when the programmer then ships the executable, and the poor user who has less memory reaches this part of the program, and the new call fails and returns null. Assert, however, is no longer in the code, and nothing happens with the pointer that points to null. As soon as the statement pointer cat some function is reached, the program crashes. Getting null back from a memory assignment is not a programming error. Although it is an exceptional situation, your program must be able to recover from this condition, if only by throwing an exception. Remember, the entire assert statement is gone when the bug is undefined. Exceptions are covered in detail day 20. So there are side effects. It is not uncommon to find a bug that appears only after the instances of assert are removed. This is always due to the program unintentionally depending on side effects of things done in assert and debug only code. For example, if you write assert equals to 5, you're testing whether x is equal to 5, you can create a nasty bug. So make sure you use assert correctly. You could also have class invariants. Most classes have a certain condition that could always be true whenever you are finished with a class member function. Class invariants are the sine qua non of your class. For example, it might be true that your circle object should never have a radius of 0, or that your animal should always have an age greater than 0 or less than 100. It can be very helpful to declare invariance methods that return true only if each of these conditions is true. And you can use assert invariance at the beginning of every class method. The exception would be that your invariance would not be returned before your constructor runs or your destructor ends. So here they demonstrate how to use invariance. They just say, where's their invariance? Okay, so here they have an invariance const, right? So what do? They assert invariance. And what does this tell us? It basically tells us that, here's what it tells us. The assert macro is defined, right? If the bug is found, this writes an error message. Okay, so string class invariance is declared. It's dependent on lines 143 to 150. So 143. So here, this is the string class of invariance, right? So they created an invariance class, and they assert it to be true. So when the invariance holds true, what do they do for the invariance? Okay, so here are the invariants. It defines if it's show invariance and string tested okay. Otherwise, return length and string, and not length and not its string. So its string is the what is its string? its string is a character pointer, so while I guess it's not null. So it's just, this is just testing if the string is valid. So the remaining class function calls invariants before any action is taken, and then again before running. This affirms and validates the principle of C++ member functions other than constructing destructors should work on valid objects to leave them in a valid state. Class animal declares its own invariance method implemented on lines 189 to 195. Note on lines 155, 158, 161, and 163 that inline functions called the invariance function. So printing interim values. Assert something is true using the assert macro. You might want to print the current state of pointers, variables, and strings. This can be very helpful in checking your assumptions about the progress of your program and in locating off-by-one bugs and loops. So here they illustrate this idea. They just print out whatever. They have a preprocessor called print, and that just prints out the value of x. And they do that to print out all the values of here. Okay, so macros versus functions and templates. Macros suffer from 4 problems in C++. The first is that they can be confusing if they get large, and they could be difficult to manage. Another problem is that macros are expanded inline each time they're used. This means that if the macro is used a dozen times, substitution occurs a dozen times, and that could be inefficient. In fact, they are expanded inline leads to the third problem, which is that the macro does not appear in the intermediate source code used by compiler, therefore is not. Okay, the final problem is that it is the biggest. Macros are not type safe. Okay, although it's convenient that absolutely any argument can be used with a macro, this completely undermines the strong typing of C++ and is anema to C++ programmers. Okay, so yeah, that's a problem. That's just about. Okay, so we can also talk about bit functions. So in hardware devices and low devices, they're basically each hardware device has like a certain number of bytes, right? And each byte has 8 bits, and in a 4 byte long, you can hold 32 flags. A flag just tells you the state of your object, of what is going on, is it on or off. So if a bit is set, its value is 1. If it's not, it's 0. So think about like how circuits work in your computer. Circuits work like on and off. So if it's 1, it's on. If it's 0, it's off. That's that's also how binary works. So you could set and clear bits by changing the value of long, and that can be very tedious. But here's how it works. There's something called AND, OR, NOT, XOR. Okay, so you could set each bit. So here's basically how you set each bit. Okay. Okay, so I'll just explain how this works. Okay, so here, okay, so you could express each number into binary, right? And a binary is 1 is on and 0 is off. So you could actually set each bit by doing this. And how do you do that? So what does that mean? If I want to change a bit to on and off, I have to do something to it, okay? So there's an operator of AND. Basically, AND returns 1 if both bits are 1, but 0 if both bits are 0. The way to think about this is that the result is 1 if a bit is set, and if the bit 2 is set, otherwise the result is 0. Okay? So they both have to be 1 for it to be 1. If it's 0, then they both are 0. Okay? OR is different. OR is the logical bit operator of OR. This is a single bar. Okay, so and it was the ampersand, by the way. This is the ampersand, right? For OR is different. It's just this bar thingy. Like it's underneath the backspace on the keyboard. It basically is an OR, and it sets a bit. When you OR 2 bits, the result is 1 if either of them are 1. If neither of them are 1, the value is 0. Okay, so bitwise, there's also exclusive OR, which is XOR, and that's if both of them are ones, it evaluates to 0. Otherwise, they're all ones. Okay, here I'll just explain this. It makes more sense if I do it this way. Let me just get paint out. Okay, so for and, this is and. Alright, so if I have 1, 0. Okay, it makes more sense if I just say it in the true-false table. So if you guys learned from grade school, remember how you have like a true-false table, like A. This is just how logic works. A, B, and then you have A and B, and then it was like A or B. I think you guys learned this in geometry in high school or something. So basically, if one is true, there's a bunch of conditions you could have. True, true. A is true, B is false. This time A is false, B is true, and then they're both false. Right? Well, for and, remember, true, true is still true. If there's one false, they're all false. So because A is true and B is false, it's false. If A is true, A is false, B is true, it's still false because there's a false in this statement for A and B, so it's still false. And because it's false, false, it's still false. A or B. A or B is different. True, true is true, right? We already know that. True or false. True or false, it's going to be true. Because you have one true, right? That's true. So that's why it's true. False and true is still true because you have one true, that's why. False, false is still false. So yeah, that's basically what it is. This is how bitwise this is how it works, right? So now we're going to talk about how it works in memory. This is exactly the same thing. So I'm going to just make this smaller. It is exactly the same thing how you learned in grade school. So if you want to have, let's say you have, just replace true with 1 and false with 0. So if you have A and B, it's the same thing. A and B, and then A or B, and then we're also going to talk about XOR. It's XOR is like XOR. Let's see. Yeah, XOR is this. XOR is this. It's not an exponent sign. Yeah, well, on the keyboard it is. Okay, so how does it work? Well, replace everything with true. Okay, so it's the same thing as true, false, right? We replace true with 1 and false with 0. So you have 1, 0. Oh, no, my fault. Ah, damn. My fault. So you have 1, 1, 1, 0, 0, 1, 0, 0. Okay, so you have true. These are the same things. 1, 0. Because it's 1, yeah, okay, this is 0. This is 0. Or, same thing. Just, this is 1. It's 1. Therefore, because one of them is 1, you have, the answer is 1 for OR. And here. XOR is different. XOR, if it's 1, 1, it's 0. That's what XOR is. And then, if it's 1, 0, it's and everything else is the same thing as an OR. So yeah, that's basically all what the bitwise operators are. And, or, XOR, complement. Oh yeah, complement is it just flips all the bits. So every ones becomes zeros and every zeros become ones. Okay, so yeah, that's how it works. That's how all the operators work. So here they set 120. Okay, so here they have 128 become in binary, which is this number in binary, and the result, the value of it is 128, right? So here is this result. Bit is clear. They clear it out by ORing with 0, 0, 0. And then bit 8 is set. Wait. Yeah. Wait. I'm not sure what they're doing here. Yeah, so that's basically how it works. To clear a bit, you could end the bit with the complement. Flipping bits. XOR it by 0, 0, 0, 1, 0. And that helps you. Yeah, that's basically how it works. What are bit fields? So under certain circumstances, every byte counts. Saving 6 or 8 bytes in a class can make all the difference. If your class or structure has a series of Boolean variables or variables that can only have a small number of positive values, you might save some room using bit fields. So the smallest type you can use in your class is a type char, which might be just 1 byte. That's in standard C++. You will always end up with an int, which is most often 4 bytes on a machine with a 32-bit processor. By using bit fields, you can store 8 binary values in a character and 32 such values in a 4-byte integer. Here's how bit fields work. Bit fields are named and accessed the same way as any other class member. Their type is always declared to be an unsigned int. After the bit field name, write a colon followed by a number. The number is an instruction for the compiler as to how many bits to assign to this variable. If you write 1, the bit represents either the value 0 or 1. If you write 2, the 2 bits are used to represent numbers. Thus, the field would be able to represent 0, 1, 2, or 3, a total of 4 values. 3-bit field can represent 8 values, and so forth. So here, where did they have it? Where's a bit field? Where's our bit field? Okay, so line 4 to 7. These serve to define the possible values for the bit fields within the student class. So lines 4 to 7. These are the possible values for the bit fields. This is an enum though. It's strange. Okay. Student is declared. Okay, so what's interesting is that all the data is packed into 5 bits on lines 24 to 27. So 24 to 27. Oh, okay. So all the instance variables are defined as 5 bits. 1, 2, 3, 4, 5. Okay, so I have 1, 1, or 2. First bit represents the student's status, full-time or part-time. Second bit represents whether there's an undergrad. Third bit represents whether the student lives in a dorm. Final 2 bits represent the 4 possible food plans. The class methods are written as any other class and are in no way affected by the fact that these are bit fields and not integers or enumerated types. The member function getStatus reads the Boolean bit and returns an enumerated value. This is not necessary. It could just be as easily written to return the value of the bit directly. So here they just return my status, and status just returns a bit, I think. And then they have the stat. Okay, so yeah, you could just simply print out this. This is basic programming style. Just remember to use tabs. Remember you put your braces correctly. R's tab. R structure like this. Put tabs. Use white space to help readability. Don't use spaces between objects and arrays and then pair operators. Name your identifiers. Avoid abbreviations. Yeah, these are just obvious stuff you should know. Use comments. Setting up access. Use include files. Oh yeah, the next step. I just keep programming. Just get advice. Just search online and related topics. We might go over data structures later on. I don't know if I'll set that, but yeah, that's basically it. Thank you guys for this long journey of C++ in 3 weeks. I hope you guys enjoyed this journey. I hope you learned something. Anyway, rate, comment, subscribe. I check you guys later. See ya.